Stanford University.
Okay, hi everyone. It's exciting, right? We're in week 10. Everyone's really excited for the end of the class. Well, thank you so much to the people who did turn up in person to see this last week's lecture. I guess Richard and me both have one lecture each, with me doing the Tuesday and the Thursday. I suspect that there are probably a few people who we won't be seeing today who are trying to catch up on their final projects. I'm sure every one of them will watch the video and catch up on what they missed during spring break. But for those of you who are here or watching, here's what we're going to have today. So I wanted to sort of try and say a little bit about sort of bigger picture solving needs of language and where things might be heading or should be heading. I wanted to kind of come back and say a bit more about some of the tree structured model ideas and how those might be reinterpreted in a different context at the high level of language. And then something that's in the same vein as that is for our research highlight today. Jody is then going to be talking about this kind of interesting model out of Berkeley for learning to compose for question answering. And then, for the end part of it, there are kind of a couple of things that we haven't said very much about in the class, which I thought I should just say a bit more about before the class ends. So we'll talk about character-based models. Okay, quickly the reminders. Well, best of luck in finishing your assignment 4 or your final project. There's sort of a subtle balance, but in terms of what you're doing, you should be making sure you kind of have solid baselines and well-trained models. It's obviously good to be investigating fancy architectures, but if it's sort of if they're sort of not working at all, or it seems like they're working very badly, it's sort of always hard to kind of work out where things are. So, especially if it's a different problem, well, you sort of want to know, well, how much would you get if you just ran a bigram logistic regression on this? And then is there reasonable evidence that this neural model is well trained? So it's not that you have to sort of infinitely tune your hyperparameters, but we sort of hope that you have sort of reasonably solid models. If you're having any problems, do try and get some help. I know there are a lot of people going to office hours today. So tonight, Richard is again having infinite project office hours. So feel free to come by. Depending, you could either go home and have dinner and come back at 10 p.m. probably, and he'll still be there. Make sure you're in the queue. And then sort of finally for Microsoft Azure. So Microsoft's really been super generous at giving us more GPU hours. And so we've got a fresh new allotment of GPU hours. And I guess this afternoon I was trying to top up various people's accounts. But in general, it's kind of easiest for everybody if your account doesn't run out of credits, because then it gets cancelled and you get locked out and we have to reactivate it and blah, 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 blah. So, really if you sort of know you want to do something that takes more credits than you have, feel free to get in contact on Piazza beforehand. Preferably don't just email me, because in the good case, one of the TAs, James or Nish, do it rather than me. Okay. So a kind of interesting thing that's happened in the last couple of years is that a lot of the key deep learning people have really sort of redirected their mission with this idea that they could sort of solve language. So historically, most of deep learning came out of vision, and vision really dominated in deep learning. But for a couple of interesting reasons, the same people that were the sort of most key deep learning people, such as Jan LeCun and the others of Jeff Hinton, Yoshua Bengio, really they've all considerably redirected their research programs towards language. And so here's just sort of one random sort of Business Mag quote from businessinsider.com, which shows how this is sort of panning out in practice. So Jan LeCun is quoted as saying, "The role of FAIR, Facebook AI research, is to advance the science and the technology of AI and do experiments that demonstrate that technology for new applications like computer vision, dialogue systems, virtual assistants, speech recognition, natural language understanding, translation, things like that." And the thing that's sort of really surprising about that list is, well, okay, the first application he mentions is computer vision, and he's a 20-year computer vision guy, so that's maybe not too surprising. But if you keep on reading after the first application, every other application he mentions is a natural language application. Dialogue systems, virtual assistants, speech recognition, natural language understanding, translation, they're all language applications. I think coming off of that, that sort of many people who haven't been long-term language people kind of feel that language will have a kind of an ImageNet moment where somehow someone builds a big enough, complex enough neural network that kind of the task will just be sort of measurably solved in one step. I kind of think actually that's probably not going to happen, because I kind of think there are so many different language phenomena and tasks that there's sort of just no one task that can really sort of have the same kind of seminal, okay, we've solved natural language understanding. And so I wanted to, with respect to that, sort of mention a couple of things of what has been lost from old NLP work. Because I think there's actually kind of an interesting contrast if you go back to the sort of good old-fashioned AI work in natural language processing versus a lot of what you see more recently. And that is that if you sort of look back and sort of 80s, 70s natural language processing work, that these people had really lofty goals, that their goal was to sort of really have human-level language understanding. Now, actually, what they could do was extremely, extremely modest. But nevertheless, the contrast is, it sort of seems like here we are today, we have much better realities as to the kind of things we can do. But it's not always clear that everyone's reaching for the stars, as opposed to just thinking, okay, well, we can run an LSTM on this language data, and that'll sort of work reasonably well, and not try to get beyond that. So I thought it might be good just to have a few slides at the beginning, sort of looking at a bit of older NLP work and seeing if there are things that we could kind of see and learn from that. And so I chose as my example Peter Norvig's PhD thesis. So probably most of you vaguely at least know who Peter Norvig is because of the textbook on what is it? Artificial Intelligence, A Modern Approach, Russell and Norvig book. He's now he's worked for many years as a director of research at Google. And so it's just past the 30th anniversary of Peter's PhD thesis, which was in natural language understanding. It was called A Unified Theory of Inference for Text Understanding. Okay, well, what do you find if you look in his thesis? I mean, in terms of the actual language processing and language understanding that's in the thesis, I mean, in some sense, there's shockingly little of it. So in his for the work for his entire thesis, there's only one piece of real natural language that's analyzed in the entire dissertation. All the rest of it is sort of toy examples like Bill had a bicycle, John wanted it, he gave it to him, and trying to analyze stuff like that. Actually a bit reminiscent of the kind of baby sentences that Facebook AI research lately came out with. But this is the one piece of real natural language that's analyzed in the dissertation, which comes from a children's story. In a poor fishing village built on an island not far from the coast of China, a young boy named Cheng Li lived with his widowed mother. Every day, little Cheng bravely set off with his net, hoping to catch a few fish from the sea, which they could sell and have a little money to buy bread. But the interesting thing is these are sort of some of the things that Norvig said we should be able to get out of this text. And I think many of these, or at least half of these, are things that we're still not very good at. And that's actually the first half. So he's hoping to get out, there is a sea which surrounds the island, is used by the villagers for fishing, and forms part of the coast of China. So those are sort of interpretive understanding of the relations that are involved. and in particular, the relationship between the sea and China is quite distant in the text, and it's sort of mediated by the existence of the coast. That's the kind of stuff we're still not very good at. Cheng intends to trap fish in his net, which is a fishing net. Again, that's sort of interpretive stuff, right? So there's sort of this leap of, he set off with his net hoping to catch a few fish from the sea. So it never actually says that he's going to catch the fish with the net, but any human being would interpret it that way. And again, that's sort of the kind of interpretive language that we still aren't very good at dealing with. The other two are actually much easier. The word which refers to the fish, the word they refers to Cheng and his mother. We talked about things like that. So in terms of how he's going to do this, I mean, interestingly, the kind of perspective in the 80s was just completely diametrically opposed to what it is these days. I mean, in the 1980s, it was sort of believed, just as an assumption that was beyond question, that the only way that you were going to do any kind of natural language understanding was to have a knowledge base that you could work with and reason on. So, on page 4 of the thesis, he takes it as established, as we have just seen, a suitable knowledge base is a prerequisite for making proper inferences. And that was sort of just no more of an argument than, look, we need to make inferences between these facts to understand that the net is going to be used to catch the fish, therefore we need a knowledge base to do it over. Whereas sort of what's happened in the last 2 decades is to sort of show that there's actually a lot of natural language understanding that you can do without having any knowledge base and just working on fairly surface forms. So in his thesis, he outlines 6 forms of inference and tries to build a natural language understanding system that embodies them and will be able to make inferences over that passage. 2 of them come in pairs, so there are 4 basic types. So one is elaboration, and so that's working out how to connect 2 entities. So this example is John got a piggy bank for the reason of having money, for the reason of buying a present. But the example from the previous slide was he had the net with him for the reason of helping catch the fish. And so you have to sort of do this contextual elaboration. The second one is reference resolution. That's really the only one of these that we've talked about. And we know how to do that one, and we can do that one pretty well today. The third one is related to sort of the interpretation of metaphor and abstract forms from language. So that if you have a sentence like the Red Sox killed the Yankees, that doesn't mean that they went out murdering them with knives and guns. It means that they defeated them convincingly. And so language is full of that kind of metaphor, that all the time we're sort of using physical metaphors which are having these sort of abstract interpretations. And so another part of his dissertation was sort of trying to work out how you derived those abstract interpretations. And then the third one is sort of an interesting one that a lot of the time that I think we don't think of as much, but it's actually, I think, quite important, and that's concretization. And so this is how you sort of go from a general description to a much more specific form of it. So if you know someone is traveling in an automobile, then you know that the kind of traveling that at least one of the people is doing is driving the automobile, at least until our autonomous cars get a bit better. And so there's that kind of concretization that you'll need to sort of be able to do more fine-grained inferences in the state of knowledge. Okay, so that's kind of interesting. There are ways in which we've made enormous progress. I mean, so in Norvig's thesis, the situation is essentially that they don't have syntactic parsers that's good enough that they can actually parse sentences they'd like to parse, like that story. So he describes how Walensky, that's his dissertation advisor's, Fran program was used where possible to parse sentences, but for some input, Fran was not up to the task, so we constructed the representation of the sentence by hand shorthand instead. Well, you know, we're actually better than that. We can actually parse sentences pretty well now. But once you're starting to do the kind of elaborations, to do the sort of things that were being talked about as other goals, these are kind of things that most of NLP still hasn't gotten to and maybe should be starting to get to. So I think there are still sort of big things that we still need to do in NLP. You know, on the one hand, I mean, it's just true that in the last few years, you know, there's been these exciting times and a lot of systems have gotten a lot better. And there's sort of this sense that bio-STMs with attention are sort of taking over the field of natural language processing because you can try them on any task and they work better than what people used to do. And, you know, you can even use them for surprising things. You know, you can just use a bio-STM for attention as that's going to be your natural language parser. It works surprisingly well, right? So they seem good. Another thing that's really exciting that's happened is these neural methods have just clearly led to a renaissance in language generation tasks. So any task where you actually have to generate pieces of natural language, whether that's the sort of generation side of machine translation, the generation side of dialogue, answering a question, doing summarization, that all of those fields, the generation side of things was sort of fairly moribund in the first decade of the 2000s, where now it just seems like we have these fantastically good neural language models that we can configure in different ways, and we can do really exciting and nice language generation. All those fields have sort of been springing to life lately. And it's also a sort of super interesting time scientifically, because I think sort of for most of natural language processing, there's just sort of been this assumption that we need to be building particular kinds of representations of language and working with them. So we want to have sort of syntactic representations, and often we want to have above those things like semantic frames to represent events and relations in language. And so we're sort of building explicit localist language knowledge representations, whereas what some of the recent work, such as the stuff that Richard was talking about last week, was showing is that it now seems that there are a lot of situations in which we can build these end-to-end deep learning systems that don't have any of these kind of explicit localist knowledge representations, but actually work very nicely. But on the other hand, you know, there are a lot of things that we still, I think, have barely scratched the surface of. So one of those is we still kind of have very primitive means for building and accessing memories or knowledge. So yes, there's been a lot of work with LSTMs, where the M is memory, and memory networks and other things like that. But really all of those are models of sort of very recent short-term memory. That's the ST and the LSTM. That they're not really models of how, like human beings, that we can have years of experience of our lives stored in our heads, and we can flexibly sort of bring forth relevant facts at the right time. That, you know, all they're doing is a sort of linear scan of what's happened in the last 100 words or something like that. So that's pretty poor. Another thing that's pretty poor is we don't really have much in the way of models that let us formulate goals or formulate plans. And really, if you're going to do a lot of things in conversation, like have a meaningful dialogue, you sort of have to have some goals and plans. That yes, you can just be shooting the breeze, but a lot of the time you want to accomplish things which leads to subtasks and things like that. Another area where we're still really bad is we're just sort of pretty bad at intercentral relationships. So once we're inside one sentence, the structure is usually pretty clear and we can work with that. But once we sort of try to reason between sentences or between clauses and understand the relationships, we're usually pretty poor at that still. And, you know, we still can't do many of those things that Peter Norvig was talking about, right? That if we want to do elaborations in a situation using common sense knowledge, that's not really the kind of thing that we've been able to build deep learning systems to do so far. Okay, so that's the end of part one. So for part two of today, I wanted to sort of say a bit more about tree-structured models, and then sort of talk about a bit of recent work that was done by a recent student of mine, Sam Bowman, along with John Gauthier, on sort of having more efficient ways of doing tree-structured models. So for my linguistic self, I still think sort of having these sort of constituent pieces that you can build representations of, which gives you a kind of tree structure, is roughly the right kind of model. And so up until now, I'd sort of shown some examples of bits of syntax and looking inside the sentiment of clauses. Here's another nice example that was some work that was done at Maryland by Mohit Iyer and his fellow students. And so what they were wanting to do is be learning models of the political ideology of pieces of language. And so pieces of language could either be neutral, which is shown in gray, or they could have liberal or conservative pieces of political ideology. And that wasn't just done at a sort of a whole paragraph or sentence level. In particular, they were able to sort of build this kind of hierarchical constituent model where you could label pieces of rhetoric or ideology as conservative or liberal inside sentences. So we have examples like this one. They dubbed it the death tax and created a big lie about its adverse effects on small businesses. And so the model is picking out death tax as a term of conservative ideology and its adverse effects on small businesses, so that's conservative ideology language. But then when you're sort of putting that together, interestingly, it seems to have learnt that putting scare quotes around death tax, it then regards that as a piece of liberal ideology. But beyond that, once you get up to the whole sentence representation, when it's they dubbed it the death tax, that's then being regarded as a sort of a piece of liberal ideology of representing the opposite point of view. Here's one other example that shows the same kind of thing. But taxpayers do know already that TARP, so that was the sort of recovery program at the beginning of the Obama administration, was designed in a way that allowed the same corporations who are saved by huge amounts of taxpayer money to continue to show the same arrogant traits that should have destroyed their companies. So this bit here, the huge amounts of taxpayer money is being identified as conservative ideology, and then it's being embedded in this sentence, which is again showing liberal ideology. Yeah. I cannot explain that. I mean, it seems like it should have been colored gray. Yeah. These models aren't always perfect. They try. There's some inference or something. Yeah, I don't know. And even saved, it's not very clear. That's what we get out. Okay, so those were our kind of tree-recursive neural networks. So I think they're theoretically appealing. They can be empirically competitive, especially if you don't have 100 million words of data to train on. But in most circles, they've sort of fallen out of favor, and that's because they have some big disadvantages. So they're often prohibitively slow. Most often, they've been used with an external parser, although you can use them to parse as you go, but I guess that contributes to them being prohibitively slow. And you could also think that although there's something nice about these tree-structured models, you might actually wonder if are they missing out on something, because even though it makes sense that there's sort of this tree structure of language, language does also have a linear structure. You do sort of say these streams of words that go left to right. And something that people have often observed is if you only have tree-structured models, you then have words that should be very close to each other that end up very distant from each other in any kind of tree structure. And so actually the model I'm about to talk of ends up having both tree structure and linear structure. Yeah, so why are the tree-structured models so badly performing? And essentially the reason is they're not well suited to the kind of batch computations on GPUs, which is really the sort of centerpiece of what's allowed sort of efficient training of large deep learning models. So if you have a sequence model can only have one structure. You're going from left to right and you're computing hidden stuff above each word in turn. And because of that, you can take a whole bunch of sentences, preferably of similar lengths, and run them through lockstep in this sequence model, and that's really efficient. And the problem is, if you want to do that with tree RNNs that you get this input-specific structure, that every sentence has a different structure, and so that undermines your ability to do batch computation because you're sort of trying to construct different structural units in the different sentences. And what happens with GPU code, if you've got a batch of sentences and each one has different structure, what it does is sort of your 32 threads, one of them is computing and the other 31 are idle every time that there's something different being done on one thread versus the other threads. And so that kills all your efficiency. So Sam and John and co were sort of trying to then work out, well, could we come up with a different form of model which is at least closer to the efficiency of a sequence model while still giving us the benefits of tree-structured representation. And that led to the shift-reduced parser-interpreter neural network, or SPINN model. So the base model is equivalent to a tree RNN, but because it's better for batch computation, you can't completely get rid of the fact that they're different structures, but it's better for batch computation. It can be sort of 25 times faster or more, depending on the kind of data. And it also provided an opportunity to do a sort of a mixed linear and tree-structured model that can be used alone without a parser. So it's kind of a nice integrated model. I just want to show you a bit of that. And the starting point of it is essentially exactly the same as the dependency parsers that we saw in assignment 2 and in class. So for any piece of tree structure, you can describe a tree structure as uniquely as a sequence of shifts and reducers. So for this structure on the left, right, you're going to take the and cat shift on twice, then you reduce them once to put them together, you shift to get sat down on the stack, you reduce once, you reduce the second time, and so this sequence of shifts and reducers corresponds to this tree structure, and every other sequence of shift and reducers, well, either corresponds to a different tree structure or is invalid, right? If you start off trying to reduce before you've got nothing on the stack, you can't do it. And so what we can do is that we can build a model that's sort of acting like a transition-based parser in shifting and reducing. And so it's going to have a sequence model in the middle of it. But that sequence model is then going to be looking at a buffer of words yet to be dealt with and maintaining a stack. And inside the stack, there's going to be composition, kind of like a tree RNN, well, not really kind of like, exactly like a tree RNN, which will build tree RNN representations. So at each point, our LSTM model is tracking along, and it's predicting which thing to do, reduce or shift, kind of just like the dependency parsers that you build. And so depending on what it does, when things reduce, you're then doing a composition operation on the stack, which is reshaping the stack. And well, having this tracking LSTM is both a simple parser and it gives us this kind of sequence context that we can just sort of also model the sequence of words. So the essence of getting this to work well is how can you implement the stack efficiently? Because if the stack was just like this and you've sort of got a stack for each time step and the stack changes, well then you'd use a vast amount of memory in the stack because you've got a different stack, different complete stack at each time step, and it would also be bad for achieving this lockstep advance that will make computation efficient on a GPU. So that's sort of bad in various ways. So the secret of getting it to work pretty well is to say, actually, for each sentence, we're only going to have one stack, and we're going to incrementally sort of build up representations on the stack as we go. And so it's using an efficient kind of data structure, which is similar to data structures used elsewhere. They're sometimes called zipper data structures and things like that. They're also used in programming language techniques. So the idea is like this. So we want to build up the structure of spot sat down. And so when we start shifting, we have this one stack which we start shifting words onto, spot sat down. And so there's only ever one stack, but then on this side, we maintain some back pointers. And these back pointers, read from right to left, is sort of telling us what's on top of the stack. So at the moment, 3 is on top of the stack, followed by 2. So then when we do a reduce operation, we don't delete things off the stack, we just write a new thing onto the stack. So we compute using our composition operation in a tree-RNN style, a representation for sat down, and we simply change our back pointers and say, okay, now we've got 1, 4 on the stack. So 4 is the top of the stack and 1 is the other thing on the stack. And so then when we again do a reduce, we compute a representation for spots stacked down, and our back pointers say 5 is the only active part of the stack. And the crucial thing is in these back pointers allow us to know what's where on the stack when we do operations. But in terms of our vectors that we're using inside our forward pass and our backward pass, all of the vectors are in this array here. And so we only have sort of one array per sentence that we're sort of incrementally building up. Yes? Yes, it does. Yeah. Well, I mean, it does need to, I mean, it clearly needs to back propagate through it, right? Because it's wanting to learn composition functions, right? So it's going to be sort of learning a matrix representation as to how to combine these two words. And then your question is how, and at that point I have to give a sort of an answer of, gee, this was done with supervision. So the reason you'd think it wouldn't be differentiable is you'd think, okay, there's a choice at different points as whether to shift or reduce. And if that's a hard decision, then that introduces a non-differentiability. Now, the way we did things in this was sort of to take an end run around that. So if we trained the model at training time on sentences that had parsers, we could compute, then there's no non-differentiability, and we could compute the composition functions, and we could learn to predict the actions. And so in some sense, that's an easy way to do it, which avoids the non-differentiability. If you didn't want to do that and you actually sort of wanted to say, let's have this uncertainty while you're learning, then you'd have to do something more complex. And that then leads into ideas like reinforcement learning or some of the other estimators that have been tried recently, like the straight-through estimator, where effectively, although the model makes hard decisions in the forward pass, you're using a kind of a soft logistic function, the backward pass, to do the differentiation. Okay, but doing this kind of model compared to a traditional compared to a traditional tree recurrent neural network is actually sort of super efficient. So this sort of shows for different batch sizes, and obviously this is going well out in the batch sizes, but sort of shows the general point that traditionally sort of tree recursive models are just sort of really inefficient, that you don't kind of get a good batch speed up effect because you've got different operations at every time, whereas the dotted line is just an LSTM, which is super efficient. And although this model starts to curve up too in the blue, and it has to curve up because you are doing different operations on the stack, it's sort of just way more efficient out to quite large batch sizes. Okay, so Sam was then working to sort of use this model on natural language inference. And I think we haven't talked much about natural language inference, but I know it's come up for some of you that look at the fake news challenge and things like that, because I and others have pointed people out of it. So the idea of the natural language inference was you have a piece of text, and then you have a hypothesis following it, and you're wanting to say whether the hypothesis follows from the piece of text. It's an entailment. So if a man rides a bike on a snow-covered road, then a man is outside. That's an entailment. Whether it's a contradiction, so if a man in an apron is shopping at a market, that contradicts a man in an apron is preparing dinner. Or whether it's neutral, which means it's neither an entailment or a contradiction. So two female babies eating chips. is neutral with respect to two female babies are enjoying chips, because they may or may not be enjoying them, even if they're eating them. And so we collected this large corpus, SNLI, of these kind of sentences. And the way we constructed it was we started off with one of the vision and language databases, MS COCO, where there was a picture and a sentence describing it. A man rides a bike on a snow-covered road. And we wanted to sort of have something where the scene was a description of a picture, because that meant there was sort of a concrete thing that the sentences were describing, so that would hope to avoid there being uncertainty of reference. But then we collected the sort of hypotheses from Turkers, and the Turkers weren't actually shown the photo, they were just shown the passage, and then they were meant to generate sentences where entailments, neutrals, or contradictions, and then we were trying to build systems that do that. And this has been a quite good task that a whole bunch of other groups have then tried to do better on. For what we were doing, we were kind of interested in this idea of coming up with sentence representations by building them as recursive neural networks. And so the models we were building was using SPINN models to build representation for each sentence, and then running it through comparison neural network layers to find the whole sentence meaning, the sentence relationships. So we have one SPINN model for representation of this sentence, one for that one, and then we're sticking it through a neural network, which is then giving a probability distribution over the three actions. So after having been through the SPINN model, we have a couple of fully connected neural network layers, and then you've got a softmax over the three decisions. And so here are a couple of results from this. So there's sort of some previous results, but the sort of things that are kind of interesting here is this is an LSTM-RNN sequence model that has accuracy of 80.6%. Somewhat surprisingly and somewhat disappointingly, over this quite large data set, so it's over 500,000 training examples, the tree model actually barely does better than that. So its performance was 80.9%. And whereas, relative to my arguments, you'd hope for more gains. But something that's interesting is having both at once, the sequence model and the tree-structured model, that actually seemed to really be rather nice and give you a kind of a nice gain on this model. I should mention that having whole sentence representations isn't the best way to do tasks like the sort of SNLI entailment contradiction task. I mean, as comes up in a whole bunch of these tasks and a lot of recent work, that if you want to do even better at these tasks, you just do better using attention models to make alignments at the word level between the different sentences. And if you do that, you can do several % better, as people have shown in recent results. But nevertheless, I think I still do believe in the sort of tree-structured idea, and you can sort of see places where having the tree representations allows you to get things right that you just don't get right in the LSTM model. So when there are finer-grained semantic facts, such as negation, gymnast completes her floor exercise, gymnast cannot finish her exercise, well then the tree-structured model is better. It also turns out to be differentially better when you just have very long examples, which the LSTM gets less good at. Okay, I finished part one, and so we now hand over to the research highlight. Welcome, Judy.
So today we'll discuss how to compose neural networks for question answering. So as a high-level overview, the papers talk about a compositional attentional model for answering questions about a variety of world representations, including images and also structured knowledge bases. The model has two components trained jointly. The first component is a collection of neural modules that can be freely composed. The figure shows actually 4 modules: a lookup module, a relate module, an AND module, and also a find module. And the second component is a network layout prediction, a predictor that assembles modules into complete deep networks tailored to each question. So our current query is what cities are in Georgia, and the figure shows the network layout for that particular query. Essentially, the model has two distributions: a layout model that chooses a layout for a sentence, and also an execution model that applies the network specified by a particular layout to a word representation. We'll start from the layout model. So in order to obtain a layout model, there are 3 steps to take. First, we want to represent the input sentence as a dependency tree. So the figure shows the dependency tree for the query, what cities are in Georgia. The second step is to associate fragments of the dependency parse with appropriate modules. So as we can see in this figure, the find module is associated with city, the relate module is associated with in, and the lookup module is associated with Georgia. And the last step is to assemble fragments into 4 layouts. It should be noted that each sentence could have multiple layouts. So for our example, one candidate layout is shown there. It's a tree structure with the AND module as the root module. And now we'll just talk about how to score the candidate layouts. So in order to score a candidate layout, we need to produce an LSTM representation of the question, a feature-based representation of the query, and pass both representations through a multi-layer perceptron. And then the update to the layout scoring model at each timestamp is simply the gradient of the log probability of the chosen layout, scaled by the accuracy of that layout's predictions. And now we'll just talk about the execution model. So given a layout as shown in figure B, we could basically assemble the corresponding modules into a full neural network as shown in figure C. And then we'll just apply it to a knowledge source as shown in figure D. And basically, we should note that immediate results flow between modules until an answer is produced at the root. So in this case, Atlanta is produced as the root, which is also the answer to our query, what cities are in Georgia. So essentially, modules are just like small neuron components that take inputs or intermediate results. The slide now is showing a lookup module whose expression is circled in red. And the lookup module basically just produces an attention focused entirely at the index fy, where you can just think of the relationship f between words and positions in the input map as some sort of string matches on the database fields. And we also have a relate module. So the relate module is a softmax that directs focus from one region of the input to another. The find module is sort of similar to the relate module. It's also a softmax, but it computes a distribution over indices by concatenating the parameter argument with each position of the input feature map and passing the concatenated vector through a multi-layer perceptron. So the last module is the AND module. Typically, the AND module is at the root of our dependency parse tree. And for the AND module, it's sort of similar to a set intersection, but it's used for attentions. And essentially, probabilities are multiplied together for the AND module. In order to train an execution model, we need to maximize the sum of log probabilities of answer labels given a world representation over a particular layout. And so our model actually achieves state-of-the-art performance on both images and also structured knowledge bases. So we'll start from looking at how it performs on a visual question answering dataset. So the model is actually able to figure out what's in the sheep's ear. It's actually a tug. It's kind of small, but it's actually a tug. And it's also able to figure out the color of the robe the woman is wearing. And for the third image, the model is not able to figure out that the man is dragging a boat, but it says the man is dragging a board, which is fairly close, so it's pretty amazing. And in terms of the numbers, so we can see the model, out of all the approaches, it has the highest test set accuracy on the visual question answering dataset. And the model can also do like general knowledge-based type of question answering. So in this case, the model is actually able to figure out what national parks are in Florida, and also whether Key Largo is an island. So also in terms of numbers, the model does really well. It actually beats every other approach by at least 3%. So this is a really amazing model, and I would definitely recommend you to take a look at the paper. And that's it. Thanks.
Okay, thanks, Shidi. Okay, so then for my remaining time on the stage this quarter, I wanted to just sort of say a bit more about a couple of things that I think have, vaguely come up at some point or another, but haven't really very prominently come up. I mean, the first one is just a sort of a very brief cameo appearance, but I just sort of wanted to say a fraction more about pointer copying models, just so that that's ideas in your head. So Richard sort of talked about a version of these a long time ago when he sort of told a bit about his group's work on pointer sentinel mixture models. But I just want to sort of repeat the sort of idea of this as a sort of one of the other ideas that people have been using a bit in recent neural networks. So one of the central papers is this one on pointing the unknown words. And this diagram's a little bit confusing to read because for some reason they sort of did it backwards. So the source is on the right side and the target is on the left side. But the idea here is so that for the source sequence, right, that we're assuming that we've run a bidirectional LSTM or something like that over the source words, and then we're in the kind of usual kind of generation LSTM where what we've done is sort of we've got some hidden state, and then we're going to be sort of starting to generate the next word based on it. And then how is that going to be done? So, we've had already the ideas that you can just sort of generate from the hidden state based on a softmax. And we've had the idea that you can kind of use an attention model to sort of look back at the source encoding and sort of use that as input to your softmax. And those are both good ideas. But in both those cases, at the end of the day, you're sort of doing a softmax over your vocabulary based on some hidden state over here. And the suggestion that's come up is that at least in some applications, and those include machine translation, but also things like text summarization, another thing that might be a good idea is if you could just decide that what you want to do is copy some word that came from the source sequence. So rather than having to sort of have a hidden state from which you can generate it from your softmax, you could just say, oh, a good idea in this position would just be to copy word 17 from the source sequence. And that might be appropriate if it's something like a name, that you might have a rare name in the input or some kind of loan word or anything like that that just makes sense to copy towards the output. And so from the hidden state, you're sort of having a binary logistic model, which is saying to what extent do you want to generate from the vocabulary softmax versus do you want to point and copy? And so this choice here, you could make it a hard choice, which would have the same kind of complications for making it differentiable. But commonly the way it's being done is just being made as a soft choice. So with probability p, you're generating from the vocabulary softmax, and probability 1 minus p, you're kind of going to look in to do another attention distribution over the source, and then you're going to just sort of be copying a word where you're placing attention. And so that's been kind of quite an effective mechanism to sort of be able to just sort of copy words from the input to the output, which has sort of helped with several applications. So in their paper, where they were using it for machine translation, having this kind of pointer model was giving them about 3.5 blue points of improved performance, which is a ton, right? A lot of the time in MT, if you can get a blue point, you think you're doing really well. So that was sort of a very big improvement. Another place where it's very effective is in summarization models, because a lot of the time in the summarization models, you are wanting to sort of copy names of people and places and things like that straight from the input to the output. But just to give a cautionary note on the other side, interestingly, in the sort of the Google neural machine translation paper that came out recently, going along with their sort of recent release of their big neural machine translation models on the live servers, that they sort of state that they weren't having much success from it. So they say, in principle, you can train a copy model, but this approach is both unreliable at scale, the attention mechanism is unstable when the network is deep, and copying may not always be the best strategy for rare words. So they don't seem to have found success with that method. So I guess like all things, you can try it and see if it works for you. Okay, so then the final thing I wanted to talk about was a bit about work that goes below the word level. So right from the beginning of this course, where we started off with is that we had words and we were going to want to build distributed representations for words, and that then led into word debug and all the stuff that we talked about there. And, you know, I think it's fair to say that sort of for around the sort of period of 2011, 12, 13, 14, that's what everybody was doing, and that's where we still start for this course. But in the last couple of years, there's now started to be a lot of work where people are going below the word level, and so I just wanted to show a bit more about that. But before doing it, just sort of a couple of slides of sort of context of how languages work. So most of the time in NLP, we're sort of, with deep learning, we're sort of working with language in its written form. You know, it's easily processed, found data. And so something that you at least sort of vaguely have in your head, that human writing systems aren't all the same kind of systems, so that they sort of vary as to their nature, so that there are many writing systems that are alphabetic and basically phonemic, which is sort of, you see what the letter is, you know how to pronounce it. Sort of something like Italian is also a fairly phonemic writing system. This example here is from an Australian language, Wambaya, but sort of it's just Gia Wu Ngangbulu, that it's sort of the sounds are just read off the letters. So that contrasts with something like English, which is an alphabetic writing system, but as anyone who's spent time learning English knows, that the correspondence between letters and sounds is much more convoluted in English. So when you have a word like thorough, it's sort of not really spelt how it sounds, that there's sort of this complex historical stuff going on. But then there are other language systems that sort of represent slightly bigger units. So some languages represent syllabic units or Moraic units. So you've kind of got a syllable like yon or ga or something that's being represented by one letter. And this is a Nuktitut from Canada. And then there are sort of the syllabic kind of languages, there's sort of two kinds. There are ones where you're having a sort of an individual letter is being used still on the basis of its sound, like an alphabetic form, and then you have ideographic languages, for which by far the dominant example is Chinese, where you're having the individual character representing a semantic component. So it also has a pronunciation, but there'll be lots of characters which have the same pronunciation, but have different meanings attached to them. And then you get writing systems that are sort of a mixture of these. So something like modern Japanese, you both have characters like these two and that one, which are, well, Moraic, that they're sort of being a kind of either just a vowel or just a syllabic consonant or a consonant-vowel form. But then you also get the kind of ideographic characters that Japanese borrows from Chinese. So you get these sort of different forms of writing systems. And then there's this question of, well, do your writing systems differentiate words? So some writing systems differentiate words explicitly and some don't. So again, Chinese is a famous example of a language that does not have any word boundaries marked in the text. You just get a string of characters. Interestingly, something that, you know, I think most people are less aware of is that if you actually go back to ancient Greek as it was written by ancient Greeks, ancient Greek was also a language that was written with no word segmentation, that the letters were just a continuous stream. So sort of putting spaces between words in ancient Greek was actually something that was first done by medieval monks to make ancient Greek easier to understand. So it was also a no-word segmentation language. So the question, was Latin segmented? So Latin, so it actually sort of varied. You can certainly find unsegmented Latin, but it started, they didn't use spaces, but it started to become common to sort of chisel a little dot between words. And so then there was a representation of word segmentation, yeah. Okay, and then when you do have word segmentation, there's still sort of some variety as to how much you segment things. And so there are kind of a couple of big parameters of variation of that. So a lot of languages sort of have little words that have sort of functional meaning, and languages vary how much they separate them or keep them together. So a language like French has these sort of little clitics for sort of pronouns, je vous ai, but they're sort of the vous for you is represented with a space, even though it sort of joins on phonologically, whereas other languages such as Arabic will sort of take the similar kinds of clitic pronouns like we and it and sort of just glom them all together and produce a slightly larger word, even though sort of different content words are space separated in Arabic. And the other big place where languages vary is when you have compounds. So all languages pretty much have lots of compounds like life insurance company employee, but in English we handily still have the spaces between the words in life insurance company employee, whereas once you go to German, that's then being written as one big unsegmented word like that. Okay. So that's the sort of context for then going below the word level. And so there are lots of reasons to want to go below the level. So if you'd like to handle a very large open vocabulary, it's kind of unappealing if you need a word vector for every word. And that's especially true in a lot of languages where they have a lot of different word forms that represent different derivational morphology, so that's sort of relationships where you sort of have causatives or possessives and other things that joined onto words, and inflectional relationships, so you have sort of different forms of person, number, and agreement and things like that. So here's a very long Czech word to the worst farmable one, and which has a lot of morphology joined together. So if you have languages like that, it's sort of unappealing to have word vectors for every word. Another place that you find things happening everywhere over modern social meaning is people use creative spellings to express a little bit more emotion. And so then you have words like good with a lot of O's in it, which probably isn't in the vocabulary of your system. And then when you want to do other tasks like translation, you often would like to go below the word level. So if you'd like to translate Christopher into Czech, you might want it to know it sort of translates into something that's sort of related, Christoph, and that sort of makes sense if you're at the character level, but not if you just have sort of these individual words. And so there's a question of how you can start to deal with some of these phenomena. So in traditional linguistics, the smallest semantic units were morphemes. So big words would be divided up into their individual morphemes. So if you had a word like unfortunately, you'd have sort of, it has a root of fortune, and then you add on a derivational ending ate to get fortunate. You add on another derivational ending to get unfortunate, and then you add on a final derivational ending, ly, to turn into an adverb, and you get unfortunately. So this kind of use of morphology has been very little studied in deep learning, though actually Richard and me had a paper with Tang Luong a few years back where we tried to use the same kind of tree-structured models to build up representations of morphologically complex words. Most of the time, people haven't done that, but have done simpler things. So a common alternative is to work with character n-grams. That's something that actually has a very long history. So back in the earlier age of neural networks, Rumelhart and McClelland proposed a representation that they humorously called wickelphones. And what wickelphones were sort of triples of letters. And so they proposed this model in some of their language models, like for representing inflections and learning inflectional forms of verbs in English, which was a model that at the time linguists reacted to very negatively. But it's an idea that's kind of lived on. So there's much more recent work from Microsoft where essentially they're sort of using the same kind of letter triples. So the picture from the bottom is actually from Rumelhart and McClellan's work. And so when you start off with a word, they represent it internally as a set of letter triples. So effectively, their intermediate layer encoder is sort of turning any word into just the set of letter triples that are contained inside it. And so that gives kind of a flat representation without needing a sequence that nevertheless captures most of the structure of the word. And it sort of works from there and can then generate another word. And this is sort of doing it explicitly with character trigrams, which are then given vector encoding. But in some sense, the idea is sort of related to when we looked at convolutional layers briefly, because they were also kind of combining together multiple letters, but it was sort of doing it after it had been turned into a continuous space rather than just separately learning a continuous vector representation for each letter trigram. And it seems to have been shown that using these kind of character n-gram ideas, whether like these wickelphones or using convolutions, can in practice give you a lot of the gains of morphemes with perhaps less suffering. Okay, and so what people have found is that you can generate word embeddings by building them up from character embeddings. And so if you're able to do that, you can then generate an embedding for any new word you see when someone sort of has some weird sequence of letters in your social media text. You can just go letter by letter and generate a word representation for it. And, in a way that should work better because it has some of the gains of that in general people argue for deep learning, that since you can then kind of have words with similar spellings should have similar embeddings. So to the extent that there's sort of different morphological forms or related words by derivation, you should be able to capture that commonality into your character embeddings. And if you're using these kind of character level models, then you kind of don't have any problems ever with unknown words because you can just represent them all. And so using character level models in the last couple of years has just proven to work super, super successfully. If I make an admission now, I mean, when the idea first came up of using character level models, I was really pretty skeptical as to whether it would work. So from the traditional linguistic perspective, that the idea had always been, well, yeah, we have sort of morphemes. We had those units like fortune and fortunate and unfortunate, that those morphemes like unfortune and it, they have meaning. But if you just have sort of letters like a U or a F, they don't seem to have any meaning. So it sort of seemed a little bit difficult to imagine that you could learn a vector representation for F and a vector representation for U and a vector representation to N, and then you could start composing them together and getting useful semantic representations for words. But what people have found is actually some of these modern models, like these LSTM models, have sufficiently powerful composition functions that actually you can learn very good word representations by building them up letter by letter. So here's a kind of a clean version of this. And so this was some work that was done by a bunch of people at CMU, Chris Dyer and colleagues. And so in some sense, you're doing the obvious thing. So for a word, what you're doing is you're running a bidirectional LSTM over the characters of the words. And so you're learning character representations and then sort of hidden representations using the LSTM above those characters. Then you append the two representations at the end of those sequences and just say that's your word representation for unfortunately. And then to sort of train this whole model, you're then embedding it in another LSTM, which is then going to give you your sequence over words for some task. So we then have a word level LSTM, which is doing something like predicting the sequence of words. The bank was closed. So you sort of have these doubly recurrent models that are nested hierarchically inside each other's. And so they tested out this model for two tasks. One was just the language modeling task, and one was the part of speech taking task, and it just works super successfully. So in particular, they were able to show better results for part of speech tagging than people had shown with word level neural part of speech tagging models. So that makes sense if you're sort of say, well, this is because we can share the similarities between words in the character level model, that makes sense, and it worked. Though, you know, initially, as I say, I was kind of surprised because it actually just sort of surprised me you can learn effective enough character level embeddings to be able to do this. I think that's a nice, clean version of this model that works very nicely. I mean, effectively, different people have put character level models in all sorts of ways. So there was slightly earlier work that was calculating convolutions over characters to generate word embeddings. I think this paper, the character-aware neural language models, came up earlier as a spotlight paper, and so this is a more recent and very complex model where they're first of all doing convolutions, and then they've got a highway network, and then they've got an LSTM network. It's sort of very complex, but again, it's a character level model. You can also do simple things. So just going right back to the word to vec beginnings, that you can sort of start off with a model that has exactly the same objective and loss function as word to vec, and just say, well, I'm going to at the top level train my word to vec model, but rather than storing a vector for each word and updating that, I'm going to, kind of like the CMU work, say I'm generating the representation for each word using a character level LSTM, and then I'm feeding that into my skip-gram negative sampling algorithm. And that works very nicely as well. So lots of stuff of that sort. And so, yeah, so these days there's just a lot of action and use of these character level models, and sort of many people are thinking it's sort of less necessary to do word level stuff. And so for my final bits, I just sort of thought I'd show you again then back to a bit of neural machine translation of the sort of a couple of the ways that people are incorporating these character level models. Or subword level models. So there are sort of two trends really. One way is to sort of build neural machine translation models which have subword units but the same architecture. And the other way is to have sort of architectures that explicitly put in characters. And so I just want to show you one example of both of those. So one idea that's been quite prominent, which sort of gets back more to having something like morphology, is this notion that's referred to as byte pair encoding. And the name byte pair encoding is kind of a misnomer, but it sort of comes from the inspiration of this algorithm. So byte pair encoding is a compression algorithm that had been developed quite separately just as a way to compress stuff. And the idea of byte pair encoding is that you're learning a code book for compression by allocating codes to common sequences. So you look at for common pairs of bytes and you allocate a code book place to them. And so someone had the idea, maybe we could run this algorithm but do it with character n-grams rather than bytes. And so this is how it works. So you start with a vocabulary of characters, and then you replace the most frequent character n-gram with a new n-gram. So if our dictionary is like this, we have the words low, lower, newest, wildest, and they occur that often, we can then say, well, we start with the basic characters in the vocab, that's them. And so now we're going to look for the commonest character bigram and allocate it as a new thing in our vocabulary. So here, the commonest character bigram is ES that occurs 9 times. So we add that to our vocabulary. And then we look again and say EST, that also occurs 9 times. Let's add that to our vocabulary. And then we ask what's still commonest. That's LO 7 times. Add that to our vocabulary. And so you keep on, you keep on doing this up to some limit. So you sort of say, okay, the size vocabulary I want to learn is 30,000 words. And so some of the things that's in your vocabulary will actually end up as words, because you will have sort of vocabulary items like the and in and of if you're doing English. But the other things that you're getting are just letters and word pieces that are kind of things that are pieces of morphology. So it's kind of an empirical way to learn a vocab. And again, you have no problem with unknown words, because at the end of the day, you have these sort of individual letters that are part of your vocabulary, and so you can always do things just with the letters. And so that kind of automatically decides a vocab, which is sort of no longer kind of word-based in a conventional linguistic way. And so then when you want to translate a piece of text, you just use that vocab and you kind of greedily chop from the left, that you chop off pieces that you can find in your vocab, preferring the longest ones first. So it's a very simple way to maintain a small vocab, but it was actually employed very successfully by these people at the University of Edinburgh. And so in the 2016 workshop on machine translation, a number of the language pairs were won by the Edinburgh team using this kind of byte pair encoding. And actually, it turns out that, again, if we say, gee, what is Google doing in their neural machine translation system, that they're actually essentially using a variant of byte pair encoding. So they've got a slightly different criterion of when to join letter sequences together that's more probabilistic rather than just count-based, but it's essentially the same kind of byte pair encoding idea. Okay, and so then the final bit that I wanted to show you is some work that Tang Luong and me did last year, which was trying to get the benefits of a character level system while also still allowing you to translate at the word level. And so the hope of this was to gain the best of both worlds by having the performance of a character level system while having the efficiency of a word level system. Because something I haven't mentioned so far is that even though you can get very good performance results by working directly at the character level, a problem of it is it tends to make things much, much slower. So if you sort of think back to that example of saying, when I said, oh, you can train a word-to-vec style model, but instead of having word vectors, you'd have a little LSTM where you build a word representation from characters. You can do that, but the difference is, whereas if you're doing standard word-to-vec training, you're just looking up a word's representation and then computing with it. If you have to run a whole LSTM to calculate the word's representation, that's a much more computationally expensive thing. So purely character-based models tend to take well over an order of magnitude longer to train, and well over and a similar kind of slowdown at runtime as well, because you sort of are going character by character. And yeah. Okay, so the question is, how can you evaluate character-based models? Can you sort of do the equivalent of word similarity? I think there's nothing that you can really do that directly does it on the characters. But I mean, you don't have to go all the way to say, let's run them in a neural machine translation system and see if it helps. I mean, the thing that people have done, and again, this has proven that character-based encoding works pretty successfully, is to do word similarity-based evaluation. So you can say, okay, let's build up representations of words using the character LSTM and then see how good the result is as a word similarity measure using the kind of word similarity metrics that we talked about when we were doing things like word-to-vec. And I think the results are that it doesn't work quite as well as the best results that people have gotten from word level models, but it actually works pretty close. And so that's again where it sort of seems to be able to be done successfully and gives you the advantages of having this open vocab. So the question is, how well do the character vectors generalize across tasks? Well, I think they generalize as well as the kind of word vectors that we train by something like word2vec. I mean, certainly people have used them across tasks for doing different things like language modeling versus part of speech tagging, and that's worked completely fine. Okay. So this hybrid model, again, it was a kind of a hierarchical character and word-based model. So the heart of it in the middle is that there's a word-level neural machine translation system. And so it was working over a fixed moderate-sized vocabulary, and so that's going to have unknowns in it. So when you can sort of generate an unknown vocabulary item, and you can sort of feed that through in the generation time. And in the encoding time, you can have words for which there are no word vectors, which here we're having it be for cute, though maybe cute would be in your vocabulary. So if you had a word not in your word vocabulary, then what you're doing is then saying, okay, well, we can do that by having character level LSTMs. And so there are two cases. So if a word is not in your input vocabulary, you can just, as a pre-processing step, run a character LSTM that generates a word representation for it, and then you'll just say that's its word representation, and you can run it through the encoder. The situation was slightly different on the decoder side. So on the decoder side, what would happen is the word level LSTM could choose to generate an unknown word. And if it generated an unknown word, you then sort of took the hidden state representation and used that as the starting point of another character level LSTM, which could then generate a word character by character. And something that we didn't do for efficiency is you might think you'd want to take the resulting meaning here and feed that back into the next time step. And that might have been a good idea, but we were interested in sort of trying to make this as fast as possible. So actually in this model, that representation was only used to generate the word, and it was still the sort of unk that was then being fed back into the next time step. Okay, so standard kind of word level beam search, and then you're doing a character level beam search for when you're spilling that one out. And so that's, again, sort of showed the strength of character level models. So this shows some results from English to Czech. And if you're wanting to do character level models, Czech's a really good language to look at because of the fact it has a lot of morphology and complex word forms. So here are some results from machine translation systems on English Czech for the 2015 workshop on machine translation. So the system that won the competition in 2015, it got 18.8 blue. There had been an entry that did sort of word level neural machine translation in WMT 2015, which didn't do quite as well. That's maybe not a condemnation of word level neural machine translation, because it turns out the winning system had been trained on 30 times as much data and was an ensemble of 3 systems. So, you know, maybe the word level NMT was pretty good by comparison. But nicely, by putting in this sort of hybrid word and character level system, that was able to sort of boost the performance of the NMT system, trained on the same amount of data as this one by 2.5 blue points, putting it well above the performance of the best system. Okay, so this then is just showing you one example of the kind of places you can win in Czech. So the source sentence is, her 11-year-old daughter, Shani Bart, said it felt a little bit weird. And so in Czech, 11-year-old is turning into this one morphologically complex word. And so if you're sort of running with a medium-sized vocabulary in a neural MT system, well, you're just going to get unks for all of this stuff, and so that's not very good. Well, one solution to that would be to say, hey, maybe we can copy. And you know, sometimes that's useful because if you can copy Shani, that's kind of good because then you just get the right word copied across. But doing copying isn't a good strategy if you're copying across 11-year-old because that sort of fails badly in generating what you want. But nicely, if you're running this hybrid word character model, you could actually get this word correct because it could actually just generate it character by character as an unknown word and give you the correct answer. Okay, done. That is my central result for today. Okay, and so remember, get help on projects. Hope you have good luck finishing. Last lecture, Richard on Thursday.